So next paper is from CPI, our friends from CPI. Gerard Charpentier, latest V-Band HPA technology.
So I'm Gerard Charpentier. I'm with Communications and Power Industries, CPI. At CPI, we lead the industry in the high-power HPA market, TWTA, solid state. We also provide a wide range of antennas. We've been contributing to the growth of the Satcom industry since its beginning, constantly innovating and bringing the best quality, the best value to our customers. We design our products in Canada, California, Pennsylvania, and Australia. We build our HPAs in Canada with a lot of vertical integration. We are experts in the high-power RF, enabling the HTS, GEO satellite, the LEO and MEO constellations, ground segments, which, as we discussed in previous sessions, are becoming more and more complicated these days. We provide high linearity RF amplifiers and block-up converters, both in TWTAs and solid state, key to high modulation, high throughput applications, combined with very high reliability for the highest customer value. Finally, we support our customers with a very strong worldwide customer-focused organization. So I will focus my presentation on V-band innovation and new ways of defining and measuring RF amplifier linearity. So here's a bit of a history of our path forward in the last couple of years from Ka-band to W-band to show you that we have technology in different types of amplifiers. Helix TWTs started in Ka-band in the 1990s with different programs, progressively going higher in power. Then we moved on to Q-band, and then these days developing V-band. Actually, we had a V-band amplifier as early as 2013 using an EIK, an extended interactive klystron, used in Italy on a program called AlphaSat. And for different applications, we went up to 95 gigahertz using also this EIK technology. Now, focusing on V-band, the state-of-the-art these days is 250-watt peak using a traveling wave-tube amplifier. You'll see on that slide a summary of the performance, the RF performance of the amplifier. As was just discussed, there are options using the block-up converter inside the HPA or adding an optical fiber interface to the amplifier. As amplifiers, TWT amplifiers use helix tubes, a good thing to do is to have at least two sources of TWTs, which is the case here for V-band, one coming from Japan and another coming from the US. So we have qualified both TWTs. Now, using V-band amplifiers, our customers have a choice. Today, the TWTA, the 250-watt TWTA, is kind of the standard, but going forward, there will be higher power tube amplifier coming up, going as high as 600 watt, in the range of 400 to 600 watt, using different types of vacuum devices called the folded waveguide TWTs. So that's on our roadmap for 2021. For these types of devices, we have an internal development in our tube division at CPI, and there are also two developments existing in France. The current state of the art for the 250 watt, I'm not going to go into detail of this slide, but you could see where we are in terms of development. We're really close to having our first HPA ready, full spec HPA. The characteristics of these HPAs is like in the solid state world. Now we talk in terms of linear power. And I'll talk more about how you define linear power for HPA in the rest of my presentation, but a common way of defining linear power is the NPR, the noise power ratio, which basically simulates a very high number of carriers. And the commonly accepted spec is 19 dB, and those amplifiers are specified for 80 watt linear power 19 dB. And it's the same performance whether you use one type of TWT or the other. Going forward, what's coming up in 2021, if these TWTs, the other type, the folded waveguide development is going forward as planned, we are being promised by the tube supplier as early as next year, high power tubes. But the difference with a helix TWT, which is very flat across the whole band, is that there will be some trade-off between the bandwidth and the power. In other terms, if you want the whole extended V-band from 47.2 to 52.4 or 52.5, you will have a 400 watt tube. If you can live with a 3 gigahertz bandwidth, you could get higher in power. So there will be some interesting trade-offs going forward. And of course, it all depends on the earth station design and the antenna technology that's available. Now, I want to talk a little bit about what's called EVM, error vector magnitude, which is a term that's being used more and more in the LEO constellations and high modulation transmission. Basically, an EVM, what is the EVM? For example, here, if you use a 16 QAM or an 8 PSK constellation, you have your symbols, and there's always a certain error compared to the ideal theoretical point for the symbol. And the error vector magnitude is the difference between the magnitude of the error vector compared to the reference symbol. So as an example, if you had an EVM of 28 dB, that would mean that your error vector is 28 dB less than the reference vector. Or another example, if you had a 40 dB EVM, that would represent a 1% error, which would be actually a very, very good linear performance. So today in the Satcom industry, there is not yet a standard for this EVM. EVMs are more used in the cellular network industry, and we will see going forward if EVM becomes a standard. But at CPI, we already have the test equipment to measure EVM, and we're already working on programs where we specify our HPAs in terms of EVM. So there are different things that affect linearity on an HPA. Commonly, we use linearizers on traveling wave tubes, or even we can use linearizers on solid-state devices. The type of modulation, the complexity of the modulation is a key factor. The number of carriers, and if you have a block-up converter in the HPA, it is as well a factor to consider. This would be an example of an EVM measurement that we did on a solid-state GaN amplifier in Ka band using 8 carriers of 250 megahertz each. Linear power is 65 watt. And the different curves in different colors represent each of the channels. So you can see that you have a little bit of a different performance depending on the channel you're using. And the lower you are in RF power, the more backup you have, the better your EVM. So if you think about what we commonly know in terms of intermodulation product or NPR, this is the same response for the HPA. You improve the EVM by having more backup. But there is something called the memory effect on GaN especially, which is a general term used for impairment of the signal if you are in multi-carrier operations. So what we found out using GaN devices is that if the interval between two carriers is beyond a certain distance, you run into this memory effect. And so one of the things that we do at CPI on our amplifiers is to apply biasing techniques on the devices and some techniques on the power supply itself to mitigate this effect so that you can actually use the amplifier at a higher linear power. So this is an example in Ku band where the orange curve is what we got in terms of IM3 performance on the Ku band 50-watt amplifier before we did the mitigation. And you can see there's a peak at a certain inter distance when you have two carriers. If you go at a certain delta between the two carriers, you will run into a peak of IM3, which will render your HPA not qualified for the transmission. So after applying the mitigation effect, we got the blue curve, which improved and got rid of that bump on the curve. So we understand the applications. What we do is when we design an HPA or provide an HPA for a certain system, one of the key questions we ask is the type of modulation, the number of carriers, and we talk to the customer about what their application is, and we apply these mitigation techniques on our GaN solid-state amplifiers. Now, on traveling wave tube amplifiers, this is not an issue due to the video bandwidth of the traveling wave tubes. This slide is to show you, it's an actual slide, an actual measurement of an EVM. So on the left part of the screen, you have before mitigating the memory effect on the GaN device, you have 8 channels that we've measured. And for those who can see the constellation on the left side of the screen, it's, you can see the 16 QAM constellation, all the 16 symbols. And you can see a certain fuzziness to the constellation, which represents the noise around each symbol. The green square is the channel that's being measured, and the EVM for this particular channel is between 9 and 16%. Now we mitigated the device, and after that, applying those techniques, we could reduce the EVM to 8 to 12%, which doesn't seem like quite a lot, but it's a logarithmic effect. And so it's actually a very big improvement of your linear performance. Here's another example of what we anticipate, or the way we characterize HPAs. And really what matters is what is the amount of noise that the HPA will introduce in the RF transmission chain. So on the left side is the blue dots are the input of the HPA. So we have used for that measurement 1 gigasymbol per second arbitrary waveform generator output from Keysight, which is actually at 5 gigabit per second using a 32 QAM modulation. And the right side of the screen is what you get at the output of the HPA. So you can see that the constellation is a little bit more fuzzy, and this is actually the effect of the nonlinearity performance of the high-power amplifier. So why is that critical? Is because if you look at EVM performance, typically you would, although there is no standard today, but the expectation is that at the input of the HPA for a very good modulation from a modem, you would have an EVM of typically 1 to 3%. And what you're actually looking at is what you get in real time. At the output of the HPA, you will have a delta EVM. If you like the EVM performance, at the output of the HPA will be worse than at the input, obviously. And then the whole challenge for us is to minimize that delta EVM. So again, this is something that is becoming more and more important in not only in Ka band, but will become more important in V band as we run into higher modulation techniques. And so in summary, in our product roadmap from Ka to V band, our goal at CPI is to provide extended SATCOM gateway capacity for high throughput application for anywhere from IFC application to IoT. And we see a new way to characterize the the linearity performance on our HPA For high-order modulation schemes, we will keep using IM3, we will keep using NPR, but now we have the addition of EVM. Not to say that EVM will replace the other ways of characterizing the linear performance. There will always be a combination of all three ways, but I see that as something that will become more and more important for these constellations. So we're at the forefront of the technology. We keep talking to our customers and making sure that whatever HPA we develop meets the expectation for these constellations. And I think that's my last slides. Thank you.